possible, so don't worry, but the values of the neutrino masses have so far eluded. When he wrote the book, I think they did not have neutrino masses yet. Or they maybe just had error bars or something. Oh dear. I see. Okay, let's see what he's saying. I see. I don't know if I would, organize the particles quite like that. But okay, let's just see what he's saying. Let's see what the string theorist has to say about particles. Each family contains 2 of the quarks, an electron or one of its cousins, and one of the neutrino species. The corresponding particle types across the 3 families have identical properties except for their mass, which grows larger in each. I see. Okay. That all of this is to say there's electron, neutrino, up quark, down quark, right? So electron, we know what that is. Electron neutrino, it's a type of neutrino. Up quark, down quark, those make up protons and neutrons. Then we come over, we've got muon neutrino, charm quark, strange quark. So it's kind of like just saying that, okay, leptons, in the leptons we have muon and muon neutrino. We have charm quark and a strange quark, which are heavier than the up quark and down quark. Then we come over to the third column. We have tau neutrino, top quark, and bottom quark. And these are, again, all heavier than the middle column. So the columns basically just get kind of heavier in the masses of these particles. But tau neutrino, those are leptons. So this is not really how I organize things, or I would organize things. I would just say that leptons are the electron, muon, tau, and the electron, muon, and tau neutrinos. Those 3 flavors of neutrinos, those are the leptons. Quarks are up, down, charm, strange, top, bottom. And then I would mention the bosons, which are the 3rd family of particles. I wouldn't really do this table, but this table does give you the masses of the particles. And yes, like he said, those masses are increasing when you go from electron to muon to tau. And I think from electron neutrino to muon neutrino to tau neutrino, and then up quark to charm quark to top quark, and then down quark to strange quark to bottom quark. So these things are heavier. Top is heavier than charm, is heavier than up. Bottom is heavier than strange, is heavier than down. Okay, or you could just have a different way of organizing the particles and kind of just look up their mass, because not everybody's going to remember every particle's mass, because there's so many particles. So it's all good, however it works. The upshot is that physicists have now probed the structure of matter to scales of about a billionth of a meter, and shown that everything encountered to date, whether it occurs naturally or is produced artificially with giant atom smashers, consists of some combination of particles from these 3 families and their antimatter partners. Okay, so the arrangement into families at least gives some semblance of order, but innumerable whys leap to the fore. So this type of sort of the particle jungle that I presented you with, if you're thinking that, oh my gosh, you just mentioned a lot of particles, electrons, muons, taus, electron neutrino, muon neutrino, tau neutrino, up quark, down quark, strange quark, charm quark, top quark, bottom quark. This is just a ton of particles and a ton of particle names, and they all have different masses. Like, what's really going on? What's the more fundamental, more broader theory of these things that can kind of subsume these particles and their theories? And can we just get to that part, because this is way too many parts. See, some people don't mind that the particles, there's this particle soup of particles, there's this particle jungle of very many particles, but some people do mind because they think that, well, learning about these particles and how very many of them there are, is it really helpful if I don't understand why these particles are a thing, and what's the sort of more broad theory that might explain all of this? So that's sort of, I think, what he's getting to here. Why are there so many fundamental particles, especially when it seems that the great majority of things in the world around us need only electrons